Thank you so much, Ryan. Thank you for the very kind words and introduction. Again, my name is Ammar, and today we're going to be walking through the design modification of an XMC-7A200 AX. That's the front I/O version of the board. So just an agenda, basically what it is. I'm going to show you the diagram of the XMC-7A. We'll then start with the design modification. We're going to be using Vivado 2019.2. I have the webpack, that's the free edition. So for the 7A, the free edition works really well. If you're going to be doing a modification for the 7K series, the webpack is not going to be very useful. Since the actual FPGA chip used is supported in the HLX edition. So we're going to be modifying or doing a modification to the example design that we provide, followed by compiling the project and producing the new MCS file. So let's start out with the 7A200 block diagram. Now, the example design has the rear I/O interface configured as two unidirectional 32-bit single-ended ports. As is evidenced over here, we've got the ports going to the P4 connector. There they are, 30 plus 2 global clock pairs, LVCMOS, that's your single-ended. The P16 connector has 17 LVCMOS and 2 global clock pairs. But the ones that we're going to be working on today are these over here going to the P4 connector. So we've got one input, one output. In this walkthrough, we're going to reconfigure the rear I/O to the P4 connector as a 32-bit bidirectional differential port. This change will require updating the block diagram, top-level vhdl source, and the constraints file. Sorry about that. There we go. So first thing we're going to do is, whether you're using this on Linux or Windows, it's going to be a very similar walkthrough. I'm using this in Windows. So in Windows, you're going to want to open File Explorer, and you want to locate the file XMC7A or the folder XMC7A200. For me, it's in the root directory of the C drive. So next, we're going to create a new folder within that folder called XMC-7A200_mod, which is highlighted right over here. Now we're going to open the example project in the root folder, that's XMC-7A200.xpr. When Vivado 2019.2, or that's the version we're using, under the file menu, we're going to select projects, archive projects, as is shown right over here. And then you're going to get this pop-up come up here. So we're going to enter C:\XMC7A200_mod for the archive location. And then we're going to go ahead and select include configuration settings, and we're going to deselect these other two. And we're going to click OK, and then we're going to exit Vivado. We're going to go back to File Explorer. We're going to navigate to the XMC-7A200_mod folder, where everything is going to be in a zip archive. We're going to open up that Vivado project. We're going to unzip the archive, and then we're going to go ahead and open up the project within this folder. So it's going to be XMC-7A200mod, followed by this folder, and then you're going to go into this folder, XMC-7A200, and you're going to open the file called XMC-7A200.xpr from within there. So when you open it, you're going to have a bunch of windows, including these. And you're going to look for the sources pane, which will display the hierarchy tab, which is shown in figure 3 over here. We're going to click the arrow symbol to the left of system_top structure right over here. We're going to click this guy over here, which then gives us what is shown in figure 4 over here. So that'll expand the hierarchy. So beneath system top are 3 components which are instantiated in system top.vhd. That's going to be AXM underscore XXX, that's your structure, system underscore I, that's your system.bd, and your Aurora. So AXM underscore VHD, that's the top level wrapper that instantiates the selected Acromag AXM module. And the selection is made by passing the appropriate value for the VHDL generic AXM module to system top. So this is configured by choosing the appropriate design run, which we'll explain later in this presentation. So what we're going to do now is we're going to open the Vivado IP integrator block by double clicking on the line that says system I, system BD, which is this guy right here. Okay. And then we have the block design open. So we're going to look for the rear I/O block, which is located at the bottom right portion of the diagram. That's why I have that red arrow pointed there. And we're going to double click on this block. When we double click on that block, you're going to get that recustomize IP dialog for the AXI GPIO IP, as shown right here in figure 6. We're going to deselect the all inputs checkbox over here. And we're also going to deselect where it says enable dual channel. Next, we're going to click OK. When we do that, the block diagram is going to change. Now, I only have a portion of the diagram shown for this purpose. That's really all we need. So what's happened over here, if we go back 2 slides, I'm going to show you something. If you see here, we've got a line going to rear out and a line going to rear in. Those are your 2 unidirectional ports that I spoke about earlier. So once we change those, we see right over here, we only have 1 line going to rear in. The line going to rear out is not there. So we don't need rear out anymore. So what we're going to do is we're going to right click on rear out on this guy right here, and we're going to click on delete. Next, we're going to click on that port labeled rear in over here, and then you're going to get the external interface properties pane showing up in Vivado. And we're going to see this is the external interface properties that's going to show up right over here. So we're going to focus on this in the next slide. So we're going to change the name from rear in to rear IO as shown right over here. Now, the block diagram should look like figure 10 with a single GPIO port named rear IO on the rear IO block right over here. We're going to save the modifications to the block diagram. You can do that by doing either Control S or selecting Save Block Diagram from the File menu. Next, we're going to click on the Generate Block Design command under IP Integrator in the Flow Navigator. That's shown in Figure 11. And that's going to generate the underlying VHDL files for the block design. So that's already highlighted for you right over here. So the Generate Output Products dialog box, which is shown in Figure 12, this right here is going to appear. We're going to click on the Generate button right here. And Vivado will display a pop-up on completion. And press OK. Oops, sorry about that. Here we are. Now, the system component and its instantiation in system top VHD file must now be updated with changes made to the ports of the rear IO block. So we're going to go to the Vivado text editor in the file menu. That's the one that I prefer to use. If you prefer to use something else like Notepad++, go for it. The path to which we want to open, first you want to open up the system wrapper to basically confirm that 2 of the ports have now been changed to 3 ports. So again, we'll go to the text editor. We'll go to the file menu. We'll find the system wrapper.vhd. Prior to the update, the system component definition included ports labeled rear in tri-I and rear out tri-O. Now the updated system component definition has 3 definitions: rear IO tri-I, rear IO tri-O, and rear IO tri-T. You'll see that in the system wrapper file. We're not going to be doing anything else with that. So next, we're going to open the system top VHD file, which is located right over here. Okay. You open that file, and we're going to go ahead and delete lines 196 and 197, which are highlighted here in blue in figure 13. Okay, 196 and 197. We are going to replace those deleted lines with the 3 highlighted lines in figure 14. Those are your tri-I, tri-O, and tri-T. Next, same file, that system top VHD, we're going to delete lines 133 and 134, which are highlighted over here in figure 15. And we're going to replace them with the highlighted lines shown in figure 16, right over here. Now we're going to go down to line 296, and we're going to insert these 3 lines right over here: 296, 297, and 298. Next thing we're going to do in figure 18, we're going to delete lines 482 and 483 in the system underscore top.vhd file. Same file we've been working in. And we're going to replace them with the 3 highlighted lines that are shown right over here in figure 19. Last thing we have to do is we're going to be adding the highlighted text shown right over here in figure 20. So from 489 to 504, we're adding all of this, okay? When we're done with that, we're going to click the save file from the file menu, or the easiest way to do it is to click on this little disk icon in the text editor, and that'll save it. So the constraints file is next. We need to update that. We need to expand the constraints file list by clicking on the arrow symbol to the left of the constraints in the sources pane. Okay, so we've clicked this, and we have now these. All right, so we'll double click on XMC-7A200 physical.xdc, and that's right over here. Next, we're going to change the single-ended signal names to differential signal names. So this is just a screenshot of part of what I'm doing here. We're going to rename the signals that are labeled RO, this, to RIO underscore P. We're going to rename anything with RI to RIO underscore N in lines 191 to 320. So you want to highlight all those lines. Additionally, within those lines, we're going to be changing what is shown as LVCMOS 25 to LVDS 25. It's actually not shown right here. I will show it. Because we need to change that. That's very important that we change from LVCMOS 25 to LVDS, because we're changing the rear IO from single-ended, which is LVCMOS, to differential, which is LVDS. First, we're going to start, like I said, by highlighting lines 191 to 320. Again, for purposes of the screenshot, all I can show is 191 to 217. So we're going to type Control-R to open the Replace dialog box. We're going to find RI. We're going to replace it with RION. and we're going to make sure that you've selected match case, match whole word, and from cursor, I believe, is default. And we're going to click on Find. You're going to get this dialog box over here, and you want to click All. You want to do Control R again for the next two instances of RO to RIO_P. Same selections, all. And the third thing we have to do is LVCMOS 25 to LVDS 25, same selections, all, and we've made the changes. As you can see in these screenshots, now we have RION, we have RIOP, and now we have LVDS 25. 64 occurrences of each have been changed. So we're going to click that Save File from the File menu, or again, we'll click this Save icon in the text editor to make our changes. So now comes the moment of truth. We're going to make sure that we did everything right. We're going to go ahead and compile the design. Now, we're going to first click the Run Implementation link under the Flow Navigator pane, which is shown right here in Figure 28. When you do this, if you've used Vivado, it's first going to synthesize, then it's going to run, and then you're going to get a dialog asking you, hey, I'm done. You want to generate a bitstream? This is the easiest way to do it. So we're going to click OK. When we click Run Implementation, we're going to get this window in Figure 29. You don't need to make any changes over here. You just need to click OK. Synthesis, as I said, is going to run first, which is followed by implementation. Sit back and relax. Depending on the speed of your computer, the age of computer, this could take a while. When I did it on my Windows 7 computer, it took about an hour to get to this screen over here. For the purposes of this presentation, everything has been screenshot, so we don't have an hour to do all this. So when the system and when the synthesis and implementation steps are complete, Vivado is going to display the dialog box shown in Figure 30. We're going to go ahead and click OK. Make sure that we have that radio button selected on Generate Bitstream, by the way. Okay. We're going to click OK to proceed with generating the bitstream. Generating the bitstream takes seconds to a couple of minutes at most. So when that bitstream generation is complete, the dialog box right here in Figure 31 is going to be displayed. We're going to click on OK if you want to view the implementation details. Otherwise, you can just click on the Cancel button. Now, the flash image, that's the MCS image, the firmware, essentially, that can be written to flash, will be created in the implementation directory for the current run. The current run that we've been doing all along has been the AXM-D01 run. So if we go to that location in the directory, which is highlighted right over here, we will find 7A200 _ AXM D01.MCS. That's your MCS file. You can use this in Vivado if you want to program the flash of the XMC-7A200. We have ways of also doing it through Acromag's example programs. You can program that in Windows over PCIe, in Linux over PCIe, as well as in VxWorks over PCIe. We're not going to go, for the purposes of this design modification, we're not going to go through with actually writing the bitstream to the flash memory. The most important thing was to basically go through and modify the design and generate that bitstream file. And that's about it. We are done with this. we're done with this part of the presentation, or we're done with this presentation for the design modification. Thank you very much.
Thank you so much, Ammar. And we also have Mr. Greg Vital here, and he's going to update us on the future topics, part 3 of this series.
Yes, thank you all for attending today. The part 3 of 3, we were going to be covering our Acropack Zinc UltraScale product offering. And what we'll do there is we'll be discussing the features of the actual Acropack Zinc UltraScale, and then some of the advantages of the Zinc UltraScale as compared to some of the Arctic 7 and Kintex 7 FPGA architectures. So I believe we have a date set for October 20th for that presentation. And
that is correct.
And at this point in time, we'd be happy to take any questions that you would have for Ammar.
Yeah, absolutely. We'll open it up for questions now. Feel free to just type them into the chat or the questions pane there in the webinar, and we'll try to field those as they come in. And if we need to go into further details, we can always have a conversation offline. So for now, we'll just wait for the questions to come in. I do have one here, Ammar, asking about the design walkthrough. Does this apply to other Acromag products?
Well, that's a good question. For the 7 series in particular, which are the XMC boards, the XMC-7A, as well as the XMC-7K, as well as the Acropack 7 series, absolutely. The architecture is going to be different for the Acropack, but the idea in general is the same. You can go in with Vivado, whatever your preferred version of Vivado is. 2019.2 just happens to be the one I've used, and those are going to be generally the same steps that you would do to change, add, or modify what you want, like we did here today. Yes, for older versions or for older boards that we have, like the Spartan, I believe that's a Spartan 6 board, the PMC SLX, XMC SLX. You're not going to be using Vivado for design modification. You'd be using xilinx ISE. So it's a bit different. It's a different method of how to do that. But our more modern stuff like the 7 series, absolutely very similar to what we did here today.
Well, I think you've done a great job explaining the walkthrough, Ammar, as evidenced by the lack of questions. But I will just say that we are available outside of this arena. Feel free to get a hold of any of us at Vic Myers Associates or on the Acromag team if you have a specific project or application you'd like to speak about. The contact information is being shared on the screen now, so you can reach out through those contacts at any point in time. And I think with that, we'll go ahead and sign off here. And just one more, just thank you for everybody who's taken the time to present today. I know it takes a lot of time to do this, Ammar, so thanks for doing that. And thanks for all the attendees for taking a little bit of time to learn about this subject. Until next time, stay safe out there.